This meeting is being recorded.
Yes. Yeah, yes. The video though. There we go. Hello everybody, how are you? Good to see you. I just turned on the YouTube live stream and we're also running into this CMU classroom at the same time. But thanks to everyone for coming. I hope that you're having a decent CMU community engagement day today. And I just felt because I wasn't running a normal math class today, I figured I should probably do something because I know that there are some people who were hoping to do some math on this Friday. And I also at the same time though, I didn't want to cancel. I didn't want to run an official class because then that would be against the spirit of the CMU Community Engagement Day. And then so what I decided to do is I decided to say, you know, I wonder if there's something I could do that could maybe feel a little bit like community engagement. And I can run a little session for anyone who's interested about what we're doing here at CMU with this NOVID app. And I thought I'd talk about this because a lot of people don't completely understand what we're trying to do with this NOVID app. And well, there are other people who do understand, who are curious what's underneath, what's under the hood, and how something like this could work. So I wanted to run this session kind of interactive, in a way where I'll say a few things, but then I want the rest of it to be able to be driven by whatever interests that you guys have. And by the way, there are two audiences watching this at the same time. There's one group, which is the CMU group, which we're talking to right here in this room. And we're also live streaming this out to anyone on YouTube who's interested. So first of all, in a nutshell, what are we doing? So this is the app that we have deployed here at Carnegie Mellon. It's called NOVID. And the principle of NOVID is very simple. It's to give a radar for COVID. And in fact, when you look at it this way, I can say it in math terms as it's a way of finding out how far away COVID is, where you measure the distance in the most relevant way you should measure the distance for a disease, which is not in terms of feet or meters or miles or kilometers, but it's in terms of the number of relationships. In particular, if you think about how you go about catching a disease like this, usually you don't randomly catch the disease because it teleported 1.5 miles to you. Usually what caused it to teleport is there was a person who lived in a house 1.5 miles away from you, who then went to class with you, and then suddenly you got it. And so this is the paradigm was, if you want to know how far away COVID is, actually the most relevant measurement is in terms of how many relationships. And then so what we did is we went and made radar. So this is actually what the app shows. So anyone who at CMU is wondering what is this app about, this app is not an app which is designed to track you. It's an app which is designed to help you track COVID so that you can avoid it. So I'm now going to play this animation. What this does is it just shows how the COVID cases might be approaching you from far away at some distance in your relationship network. Let me play it a couple of times. What you can see here is that the date changes. And as the date is changing, the height of the bar is telling you how many COVID cases there are at each particular distance. And the distances, well, this is like 6 degrees of separation or 6 degrees of Kevin Bacon meets COVID, where we then say, look, a case at a particular distance, well, that just means that that's the number of relationships between you and that person. For example, a case at distance 4 would just mean that there's a contact of a contact of a contact of a contact who tested positive. And why this is important is because actually once you show this kind of information, it changes the whole incentive structure. And that's why this is a breakthrough. And that's why we're very happy to have this happen here at Carnegie Mellon. This is a breakthrough which lets you as a student or any member of the community directly avoid getting sick. And if you want to compare this with the methods that are being used traditionally, the traditional methods based on apps are actually all designed to only tell you if COVID got within distance 1 of you, at which point it's too late. At that point, the thing is that unfortunately you've already been exposed. And if you have already been exposed, then it means that you have to already quarantine. So in fact, all of those other approaches are approaches to protect other people from you. And what we came up with is, as mathematicians, we like to think about when things are not commutative, right? Protecting others from you is a kind of app that one could make. Protecting you from others is a different kind of app. And that's what this is all about. And then the point is, how are you able to protect you from others? Actually, the secret is called just not standing in front of this part of the graph, showing the whole graph. Once you show the whole graph, once you have distance beyond distance 1, it works. That's the lead time. And actually, we're very excited about this because this could have the same impact on controlling a pandemic as the invention of radar had on modern warfare. If you're able to see something coming from far away and then do something about it, if you even think about what life is like as a student, of course, we're supposed to go with all of the best practices that we're supposed to conduct. That's definitely true. But at the same time, if you're ever interacting with people off campus or thinking about whether you might want to go to a particular gathering or a particular event, it's just really useful to know whether or not there's something hot in the area. Or even, there are things like different kinds of masks. Some kinds of masks you can throw in the washing machine. They protect us, they give you a certain level of protection. Other kinds of masks you can't, but they give you much more protection. It would be really, really useful to be able to see if something like this is happening. I also know that there's some people who are watching on the YouTube channel who might be coming from the high school student setting. And for those of you who are here at CMU, you remember what it was like to be in high school. Everyone in high school is trying to figure out how to reopen high schools right now. From a network theory perspective, which is where I come from, a high school is one of the densest networks you could ever imagine. In terms of everything is connected to everything. Therefore, if you only are telling people after they've already been exposed, unfortunately, that's going to be a bit too late and everything is going to fly through the network. And what we're doing is we're offering the ability for people to even see something coming beforehand so you could do something about it. I want to say a little thing to clarify here. Some people at CMU have asked this question. What constitutes a connection? How do you know whether or not somebody is next to somebody else? Well, that's actually pretty cool. So that one we can geek out over a few things. One of the things, the one that we're the most proud of is called ultrasound. That's the most accurate method that anyone has ever been able to make to detect whether or not two phones are around each other. And to math students, it's very easy to explain. You just have two phones. They decide that it's going to be time to play the ultrasound game, and one of them is going to make a noise. And it makes a noise. And we wait to see how long the noise takes to get heard by the other device. And they have transmitted, what time they made these sounds, and so on. Let's pretend we can measure, let's pretend we're going to do this, right? We're going to say, measure the time it takes for the sound to get from one to the other. Well, now it's trivial. Now you just go and multiply that time by the speed of sound. That's it. Okay, well, the natural question is then, how come nobody else did this? And how come nobody else does this? It sounds simple. And in fact, it's the way you find out how far away a thunderstorm is, right? Because the thunderstorm, you're like, how long does it take for the lightning to get to you? No, I just said it wrong. How long does it take for the thunder to get to you? The lightning gets to you basically almost immediately because of the speed of light. Well, the reason why this is actually not trivial, is because if you want to be able to measure the time for sound to travel from one point to another, let's think. Sound travels at approximately 1 foot every millisecond. The relevant distances for COVID tracking are like 3 feet, 10 feet. So we need to be able to measure the time it takes for a sound wave to travel with an accuracy of plus minus 1 millisecond. If you play video games, you know about ping time. And so milliseconds is like, yeah, computers can measure milliseconds. We know about that. There's a difference between ping time of like 9 milliseconds and 12 milliseconds. Well, maybe. I actually don't know enough about this subject. I just know that I've heard of these things called single-digit ping times, right? Okay, but that's with video games. With a video game, you send this ping called like a little packet of information of what you just did in the video game. But in the sound, you have to play a legit sound. It's actually back in the analog real-world realm, right? So there's an actual legitimate sound being played. You know, if you play a sound, and that sound happens to last for 0.5 milliseconds, because you want to be able to measure when it got to the other place with a resolution of 1 millisecond. If you want to play a 0.5 millisecond sound, you know what it sounds like? I can't make one. It's like, that's just too short. In fact, it's so short, you wouldn't be able to tell it apart from like someone just like dropping something. So actually, if you're going to do that sound thing I just talked about, you have to play a pretty long sound. Long in the sense of like a beep. That's long. That's long compared to 1 millisecond. In fact, that sound might be tens or even hundreds of milliseconds long. Now it's non-trivial. Because if you think about the point of view of the microphone on this side when it's recording, So there's a sound coming in, and we need to measure the start of the sound to plus or minus 1 millisecond. But the sound itself is like 100 milliseconds. Do you see where this is non-trivial now? It's because, like, from the microphone's perspective, it's like, oh, sound's coming, is ramping up. And the sound will, like, it'll like ramp up. It goes this way. It ramps up, and then it kind of stays up, and then it goes down. But you need to know exactly when it started ramping up to plus or minus 1 millisecond. It's actually highly non-trivial. It's even more non-trivial, or even less trivial, or hard. Let's just say it's even harder if you're doing it indoors, because there are echoes going around. So actually what's going on with your sound is like, it's a superposition of lots of different sounds that have gotten to you. It's adding some waves together. Okay. So in that case, what can you do? Well, it actually, so here's something that's cool. And this is an easier way to think of it. And if you like this, then you should go and study Fourier Analysis. It's spelled Fourier, F-O-U-R-I-E-R. If you're a double E, electrical engineering person, you would love digital signal processing. That's what this is about. If you're a math person, you go study Fourier Analysis. If you do applied math, you take these classes from our colleagues in the math department who are teaching this. But here's the deal. Suppose that the sound you're playing is just like a whistle. You know, like if someone blows a whistle for a while, figuring out when that whistle started is not trivial. You know what I mean? If someone just blows a whistle in a very echoey gym, it's pretty hard to tell when it started. Because how do you know, like, it takes some time to ramp up that whistle anyway. And by the way, even when you play a sound out of a speaker on a smartphone, it actually does take time to ramp up. There's no such thing as, like, give a speaker a sound wave and have it instantly start. It's actually still physical in the end. Something has to start vibrating. You know what I mean? Just like how the gym teacher has to start blowing into the whistle. But here's another way. Pretend that instead of blowing a whistle, you were playing a classical music song where just like playing a classical music song on the piano. If someone was playing a classical music song and you were able to listen to them playing to the song for like 2 minutes, you would be able to know when it started to a very high accuracy. And the reason why is because the tune is changing around. Do you know what I mean? What I mean is every single time they press a key, every new key press is letting you estimate. Let's pretend that they were on tempo, right? Let's pretend they were on tempo. Every key press gives you a new measurement of when the whole thing started. And I have lots and lots and lots of different notes coming in. Does that make sense? Like every time you change to a new note, you got a new measurement of the beginning. And furthermore, you actually know where you are in the song. Because if somebody just started playing I'm talking about a non-repetitive song. Let's pretend there's a very non-repetitive song. If you're listening to some chunk in the middle, you're like, I know exactly where this part of the song is. Actually, what I've just described is something which I had to learn as I was doing all of this. Turns out to be the principle of what's called autocorrelation. Autocorrelation is what it sounds like. Auto is with yourself. Correlation is like how similar you are. If you can come up with a song that has very low autocorrelation, then that's what you want to play. So anyway, so in a nutshell, what we're doing is that we actually had to come up with like custom types of noises to make from one phone to the other, so that we would be able to do this same kind of reverse engineering from a complicated sound wave to go and figure out exactly when it started. So that's the first thing that we do. So we use this ultrasound piece. That's actually cool, and I thought I'd share this because, you know, there is an audience who's watching this who's pretty mathematical. And that's, by the way, how we got to the first thing that we got to with NOVID. Long time ago, the biggest thing that we were proud of was we were, and we still are, the only contact tracing app in the entire world which tells you how far away the other device was. You'd consider that to be table stakes. It's like if you're supposed to be measuring whether or not people were around each other, shouldn't you be able to show how far away the other person is? The only problem is nobody else could do that, and so they don't. And then we said, let's see if we can solve this problem, and we used math and we solved it. So that and then we just put it on the front, so it's like a toy now. So like if you have the app and if you're bored, you can just be like, hey, how far away are the other people? Actually, if you do that, you'll find out that it's not perfect, because there is something called the laws of physics. Sound can't travel through people. It actually has to bounce off of things. And so you will find that the distance measured between two phones is the shortest reflected path. Now you might say, what's the point of that? Well, the point of that is, at CMU, the way we use this app is that we actually also use it for one part, which is the exposure notifications. It's like if you were legitimately close to somebody else who's positive, we actually do tell you that, because then you might want to know the quarantine. But that's how we minimize the false positives, in the sense that you don't need to worry that we might just be telling you, we think you're close, but we're not sure. Actually, if we tell you that we think you were 2.5 meters away, we're not telling you that we think you're 2.5 meters away. We're telling you that we have measured that you're less than or equal to 2.5 meters away. Because of the triangle inequality, the shortest path between 2 points is the straight line. And so since what we are measuring is some kind of a reflected pathway, we actually are extremely efficient at measuring an upper bound on the distance. And so that's actually how we ended up making this thing to be useful. So that's one of the things we use to find out if two people are close together. Actually, for the purpose of this chart, we declare that you're close together if you're within 10 meters. And the reason is because once you want this methodology of trying to avoid, trying to see things coming from far away, you want to see more things than less things. And so, therefore, we actually give you a wider net to cast your radar, so to speak. That's 10 meters. We actually also use Bluetooth, what you've heard of other people using Bluetooth to measure the received signal strength. It's like the way the Bluetooth thing works, every other app in the world, is that they use this idea of there's two phones and one's making a Bluetooth broadcast, and you want to see how long, not how long, you see how big the Bluetooth signal is that you received on the other side. Actually, I just saw that on the YouTube channel, somebody just asked, what about a lower bound? Actually, nobody has a lower bound. There's no way to get a lower bound right now that we know of. But the good news is that, lower bound meaning lower bound on distance between two people. But the good news about that is that actually we have since realized that the biggest value of this kind of a system is actually not the exposure notification. I'm going to get to that in a moment. The biggest value is the construction of the long-range network. And at that point, you see, the only reason we use the ultrasound is we want to make sure that if we're ever used to ask people to quarantine, we're pretty sure. Because we don't want to be telling everyone to just go quarantine. That just ruins your life if you're just being told to quarantine when the app couldn't even figure out how far away you were, right? But the second piece I'm going to talk about is the Bluetooth. And Bluetooth is what every other app was using. The Bluetooth principle was simple. It was like, transmit, see what the signal is when it gets to the other one. And everyone knows there's this thing called the inverse square law, right? So it should be fine. As long as you're transmitting, based on the inverse square law, you can estimate the distance to the other device, because the signal decreases proportionally to the square of the distance in a vacuum. So again, I see a lot of students in this group who are CMU math students. As we learned in the math, we learned that every theorem has like a bunch of assumptions and then a conclusion. And one of the assumptions of the inverse square law is in a vacuum. Therefore, you can use those Bluetooth contact tracing apps in space. Well, okay. We can be a bit more relaxed than that. We know that you can also use them in air, right? In air, it's also fine. Actually, let's see. What causes the signal strength to decrease? Well, it depends. Like, it has to be something that interacts somehow strongly with the frequency that's coming out. The frequency of a Bluetooth transmission is 2.4 gigahertz. That's in the band, which is similar to your microwave. In fact, it's called microwave frequency for a reason. Don't worry, it's not microwaving you whenever you use Bluetooth. There are plenty of things in the world which are using 2.4 gigahertz, like your Bluetooth headphones. They're not microwaving your brain. It's not focused enough, and it's not enough power anyway. But I said microwave on purpose. Does anyone know what's the principle of how a microwave oven works? It causes like resonance for H2O. It's like it's H2O water molecules. They resonate. It's like H2O looks. I think it's this resonation. I actually don't remember. But there's like some particular mode of resonation, if that were a word, of the H2O molecule. And so Bluetooth interacts strongly with water. But as somebody had commented on the YouTube channel, Bluetooth does just go through walls. Bluetooth actually can go through like normal walls, no problem. But if there's metal, like it's like a mirror, right? Like somehow metal can reflect waves. But metal can reflect these electromagnetic waves. That's what Bluetooth is. So, but let's go back to this Bluetooth thing, right? So Bluetooth can go through the air, no problem. Go through the ceiling, probably not much of a problem. Floor, walls. It's just if there's water, you have trouble. So what that means is like Bluetooth contact tracing app works as long as there's no water around. Now, obviously I just drank some, But even if I didn't drink water, the human body has a lot of water in it. Actually, what percent of the human body is water? Does anyone know? I don't know that fact.
I feel like it's in the 90s.
In the 90s, somebody else said 2/3, somebody else said 2%. Isn't it
Okay.
70%? You know, like the wisdom of the crowds is called just ask the question and take the median. That's actually how, this is actually a pretty good technique if you just ask a question and take the median. The median seems to be around 70% that I've just surveyed, which is probably true, especially because the people who answer later are the ones who check Wikipedia and then type it in. But in any case, it's like somehow 70%, right? Uh-oh. So that's going to say that means that the Bluetooth contact tracing app works really well as long as there's no people around. Right. And the whole purpose of it was to do something with people. So in that case, this is showing why the Bluetooth to measure distance, not so good. But then that's why we just flipped the whole paradigm. We said, you know what? What if we don't care exactly whether you were 2 meters, but we just want to know were you generally around? Because that's all we need for this network piece. Suddenly it's fine. Suddenly the level of accuracy we have is fine. And the third thing that we use is we actually also use Wi-Fi. We check whether 2 devices are on the exact same Wi-Fi access point, like the physical thing in the ceiling, for like a couple hours. And the whole principle of that is, you see, we just realized that it's better to turn the whole thing into the network theory problem instead. And now let me tell you the last piece, which is the very big observation, which is, you know, how effective is it to tell someone to quarantine after exposure anyway? Well, actually, it's very effective. If you're contacted by Carnegie Mellon or by your school to go and quarantine because you've been exposed, please do so. It's actually important because that's the way that we're trying to control the spread of the disease. But now, how would this work if it was trying to be done with an app that was not as accurate? Right? Like the thing about when CMU asks you to quarantine, actually they do some interviewing. They find out whether people were wearing masks. They find out whether you were facing each other. There's a lot of very important details in what's called manual contact tracing. And that helps to increase the confidence that when you're asking someone to quarantine, you know, they might indeed need to quarantine. But now let's go back into the app world. If you were trying to build an app and the only thing your app was doing was detecting if you were within 6 feet and detecting with this like not so accurate way, suddenly the probability that you're actually infected, if the app tells you, could be quite low. And if you dig into it, this is something that I wrote into an article, a research article I shared. If you dig into it, it turns out that probability might be really low. And when I say really low, it could even be 10%. And actually that 10% is something that comes as a consequence of the only thing the app even knew was that you were around somebody else for 15 minutes at 6 feet, if that's the only thing it knew, the chance that you would get infected from that person might actually be 10%, especially at CMU when everyone's wearing masks. Does this sort of make sense? It's like, you know, the rule anyway is that you're supposed to be wearing masks. And if you're wearing masks at school or at CMU and you're around someone for 6 feet for 15 minutes and you're not even facing each other, your chance of actually getting infected is not extraordinarily high. And another way you can think about that number, or why it's not extraordinarily high, is because you can think about how before we shut down everything, like back in February or March, if you can remember what that was like, back then, the typical person who was infected usually infected another maybe about 3 people. And now if you want to estimate what the infectiousness probability is, you take that 3 and you divide it by like how many people you interacted with for at least 15 minutes for 6 feet over the course of like 2 or 3 days. And you're not going to get a number like 90%. I mean, most people in this, especially in this community, will not only interact with like 3 people every 3 days, right? So anyway, so actually once you look at this, it actually shows that this particular approach that we're making is actually extremely powerful, because the old way of doing things is only to ask you to quarantine after you've already been exposed, which already has some fundamental issues where, for example, if a non-enforceable app tells you to quarantine, if your chance of being positive is low, the compliance rate might be low. And furthermore, it's a compliance rate to protect others from you. Whereas what we did is we said, hey, here's another way. Let's give this to the CMU community, and let's let everybody protect themselves from COVID. Let's give everyone a tracking app where it's not for them to track themselves, or not for others to track them, but for them to track COVID. And then once you build this out, if actually people at CMU started to use this entire thing as we're deploying it, we're going to build a fortress. Because if you imagine what life is like in a dorm, or even if you're off campus living with a few friends, you would get this like spider web network where you would find out if something was coming in close. And that something would be giving you the information that you need to just try to be more careful. Actually, I can give some exact examples of things I might do. I actually used to take the bus. I don't know if you guys are still taking the bus, but today, if I'm ever going to take the bus, if I knew that things were hot, I would actually probably wear a very, very careful mask if I was on public transit. And I mean like not a cloth mask. And that's not because I want to protect other people from me, it's because I want to protect me from other people. You know why I said that about the bus? It's because especially as we're going towards the winter months, the bus will probably have its windows shut. Anyone who's not a freshman may remember what the 61 buses look like at 6:30 p.m. I don't know if anyone ever took it. I used to survive on the 61 buses at 6:30 p.m. Those are the buses where they roll up and it's just jammed, completely full, right? And you could only imagine that if you actually had a COVID situation with all the doors and all the windows closed, by 6:30 p.m., the bus is going to be full of COVID. So I'm actually basically saying this is why, and actually I'm going to encourage you, if you are a CMU student, be very, very careful as you're doing all of these various things with public transit. And if you happen to see that it might not be very good, maybe try to make sure that you have a better mask, not just a cloth one. Right, but anyway, so this is what we've got. We've made something, we've put it out to CMU, we're very proud to be able to share it with the community, and it's entirely built in a way which is designed to help people avoid getting sick. And we are very happy to be able to have this chance to talk to you, because a lot of people at the beginning just assume that this app is just going to be something to tell you to quarantine when you've been exposed. And nothing could be farther from the truth. In some other universities, people are actually enjoying having this app because it helps them avoid getting quarantined. I don't know how CMU is with the quarantine housing, but there are some other universities where the quarantine housing is where people don't exactly want to be. And so this app actually helps you to avoid getting quarantined because you get to see something coming and then you be careful. Okay, well, with that, I think I'm actually going to roll into like a Freeform QA because that was actually what is the most fun part of these kinds of things. Do people have random questions? Our group at CMU who's in the Zoom, there's few enough of you that if you just want to jump in and ask a question, I'm happy to take that and then go on.
Does the ultrasound use prime numbers?
I can't quite hear you. Was somebody saying something?
1 second.
Does the ultrasound use prime numbers?
Does the ultrasound use prime numbers? We actually do have a GCD function in our code. Okay, so you know what ends up happening when the person writing the code is also a math person? I actually was the one who wrote all of the code for the iOS and the Android apps that are doing the ultrasound piece. All the code meaning all of the computational code doing the Fourier analysis. The reason why we use prime numbers is because it helps to do something related to minimizing harmonic interference. What do I mean by that? What I mean by that is that if you play music, you may know that, I guess if you blow into a French horn or something, it doesn't only make the note that you meant to make. It also makes a few other frequencies that are certain multiples or frequencies you'd probably divide. It's like half of the frequency you make. You make a few other frequencies. It's like the physics, right? Because if you've got something which has a vibration mode like this, you can also have a 2 cycles vibration mode or something like that. So now the reason why we want to minimize these harmonic interferences is because it just helps if you're going to play a very complex sound between 2 phones. You don't want to get confused where one phone's complex noises together with the harmonic interferences could get confused with another phone in the same room making some sounds. Because we actually expect this to be used like in a school, at which point there's tons of phones around and you need to have each one have its own signature sound, if that makes sense. And the reason, by the way, we have to care about the harmonic interferences is because we've also learned that if you tell a smartphone speaker to make a sound, it won't only make that sound. The speaker is a physical object too, and so it also makes some other harmonics. So yes, we have a GCD function in there. I'm actually going to hit a question that came on the YouTube, which said that somebody goes to school in person at a private school, and there's a school of 500 with 0 cases. And they're wondering, since there have been 0 cases since September, are you safe? Or should you take more measures than the school measures? Actually, I think CMU is very proud also to have very few cases. I think this is great news. So if you are in a place with very few cases, that's fantastic. But at the same time, it doesn't mean to just be relaxed, because what we're watching all the time is what's the situation as the whole COVID climate evolves. And unfortunately right now, because of the fall and colder weather that's coming through, the COVID situation is getting much worse. So I would say that whatever is the situation right now, we hope that it stays at 0 cases. That'd be fantastic. But realistically, things could go bad fast. And so what we're trying to do is we're trying to make sure everything is in place at CMU in particular. We want everything to be in place before the cases blow up. And actually we watch every day. Today there were 140 cases or something like that in Allegheny County. So we're at 3 digits again. Every day it tells you how many cases there are. And we went from 2 digits to 3 digits very recently. Are there other questions?
I think
I think there's some in the chat.
Oh, some in the chat. Oh, okay. You guys, then you needed me to read. That's really hard because my vision is not very good from this far away. All right, it's an eye test. It's an eye test. Okay. Have you found out the critical... yeah. Have you... Yeah, okay, that's cool. There's a question of what's the critical mass in order for the app to be accurate? Okay, so I'm going to share something over here. Just a second. The way I share the screen is this funny way where I like to show it behind me. So we are very careful whenever we do anything with the data we have, not to reveal anything that's private or confidential. But the good news is that people who are students at school tend to use Reddit and post stuff. So if that happens, then we can click on it. So this is from Georgia Tech, and Georgia Tech is the yellow jackets. That's the symbol over there. And somebody posted something early on when the app was starting to be rolled out at Georgia Tech. Actually, this is what we hope is going to be what you guys will be sharing at CMU soon, which says, this person says, the charts are unbelievable. What do I mean? What does that person mean? Let's go to the charts. And then they're sharing about the misconceptions here. It's like, no. This is actually a very useful app that you put in before you get COVID. So this person said it took about 3 or 4 days for them to get this chart. But I'm going to zoom in on the bottom. This is 1,000 users. So this particular person got connected to 1,000 people already. And the way they did it is, here's what the chart is. So this is not the infected person chart. Let me stand over here. This is the chart of how many people are using the app at various distances from you. So this is basically your radar's range, if that makes sense. Because if you're relying on a radar and the radar is going to tell you if there's positive things to worry about, what you care about is, does that radar have enough range? Are there enough people inside it? And so this is the beauty of exponential growth. You see, what we had analyzed when I was analyzing this was, as long as everybody has at least 2 people that they spend time with who are using the system, and if those people have 2 people that are using the system, and so on, it'll blow up. And that's exactly what happened. They have 2 roommates. The 2 roommates spent time with 3 people. The 3 people then spent time with 20 people. And then somehow along the way, you went all the way into this hump, which got into the Georgia Tech community. And then it tailed off because this was Georgia Tech deployment, not like the entire country deployment. If this was actually deployed in like an entire city, what you'd see is you'd see a continuous explosion into the exponential curve going all the way up. So the way we calculated this was, actually, it's relatively low density in order to get a picture like this. For the critical mass of being able to get signal from the CMU. So suppose you want to care about whether or not, if you want to know like, how close are you to CMU's hotspots, right? You basically need CMU to link up. And the way you get CMU to link up is if everybody had at least 2 people on it. And if you're living off campus, somewhere else in Pittsburgh, what you would care about is that sometimes you hang around with some friends. You'd want them to also have the app installed, right? And then as long as they have their friends with the app installed, you're going to link up in a channel that goes all the way into CMU. And we calculated that this is now a random graph problem. As you know, I do research in that. So random graph theory is like, when do you get a large connected component to appear? Well, in this particular case, I don't just want a large connected component. I want a large connected component where the distances are pretty close to u. And so I basically need to have a 3 regular graph. I need to have that every vertex, every person, has like at least 3 neighbors. Why did I say 3? It's because if I want a binary explosion of times 2 times 2 times 2, it's like you go in on one connection. Do you know what I mean? Like every time you go into one person, there need to be 2 ways to go out of the person. And then you go into that person and 2 out of that person. I'm actually talking through the math here now, right? So effectively what you need is you need something like 3 out of how many people do you spend time with to have this thing installed. Where the how many people you spend time with is actually like with ranges of 10 meters. So if you live in a dorm, by the way, this is extremely easy, because this actually even counts the person who's living next door to you. It will probably count the person living directly underneath you. But then what you have here is you have this big bubble. And we estimated that at a college campus, like 10% would get you something like this. And that was actually confirmed by what happened at Georgia Tech, based on what they shared in their student newspaper. Your question was a bit deeper, though. Your question said how much needs to be on this before it's accurate. So the first question I've answered here is how many people what percent do you need in order to get a picture like this? And by the way, this is our goal at CMU. This should be the goal at every other school which is deploying NOVID, is that you should get this. And it's really cool how this emerges, because this starts from, just like if you do a random graphs class at CMU, when the probability of an edge is too small, you have like a lot of disconnected things. And then suddenly there's this thing called a threshold. And once you pass the threshold, it's like, boom, everything starts interconnecting with everything else. That's what we're seeking. The next question is about accuracy of, suppose you have a signal. Suppose this thing here is reporting to be at a distance of, I don't know, 8. Oh, could it be that there's a vertex there who's actually only distance 4 from you? Well, the value here is another bit of insight from network theory. The network of interactions on a campus is very different from what's called an Erdős-Renyi random graph. It's very different from a graph where it's just like people are randomly connected to people. The network in a university is actually along the lines of a type of network called a small world network, where people are actually, so small world network generally means if I have 2 people who are connected to each other, and then another 2 people who are connected to each other, then there's a decent chance that these 2 are actually connected to each other. And that actually happens when you think about how people interact in a university. Like you go to a class, or you live on the floor of a dorm, and you have these, or you live in a house. You have these big groups which are all interacting with each other, and also people generally introduce people to other people. If you think about a school is similar. If you happen to have a school also has these like very small world networks. And so the accuracy is actually pretty good, because if you are missing a few people in between of connecting from one person to another, there are so many other redundant pathways that get from the first to the other that you just need one of the other pathways to come through. But that's actually a very interesting problem. And if anyone likes to do applied math research, actually that would probably be a pretty interesting math modeling problem to nail the exact answer. Okay, more questions. What else do we have?
It is like kind of more technical, but
Yeah,
I was
sure.
wondering if there's been any like progress with like, I know Apple doesn't allow like apps to run in the background. So if like there were any exceptions, or like you tried to get an exception for like a contact tracing thing, or if there's any progress, something related to that.
Wow, well, thanks for asking. Yes, it's true that Apple does have constraints on what you're allowed to run in the background. We were not able to get any exceptions, and we actually gave up on asking for exceptions after the countries of the United Kingdom, France, and Germany all asked for exceptions and were told no. And then we figured, well, if Apple said no to those 3 countries, it could be quite hard for us to get them to say yes to us. And therefore, because we had a lot of people on our team who are these clever, creative people from actually a lot of them were from the CMU community, we just went and found workarounds. So I'm very happy to tell you how we managed to do the workarounds. It's actually quite interesting. Although the most recent one, it's about to release, I will give the credit to that to a student at Naperville High School. In Illinois, because as I was giving these talks around the country, well, around the country means online, there was a group in Naperville, Illinois, which got really interested in bringing this to their high school. And so we got on a call, and during the call, one of the people, a really great student, said, hey, can you get this to work on Chromebooks? Because Chromebooks are, at least in their high school, like everyone had a Chromebook. So in that case, if you could get it to work on Chromebooks, you immediately can get it used in the entire school. And then we said, oh, let's try this. The next day we figured out how to do it. And as we figured out how to do it, we discovered that Chromebooks have this wonderful capability of contacting all of the iPhones nearby, even if they're in the background. So our issue before of having not much success when the iPhones are in the background was entirely resolved by the fact that the school can actually deploy the app on all Chromebooks from a single command at the administrator's point. Actually, people who are using Chromebooks in schools, the school can just say, hey everyone, app coming, and the app comes and it's installed. So you can actually deploy this app, and what the app's going to do is it's going to make sure that all the iPhones get linked up. The reason, technically, what's going on is that the iPhones are not capable of doing the following. If there's an iPhone in the background, meaning the screen is not with your app, and there's another person with also an iPhone, but the app is in the background, these two phones have no way of communicating with each other and establishing a link. But if there is any other device, including an Android or a Chromebook, which is around, that device is able to contact iPhones even if the iPhone app is in the background. So you see, it's all graph theory now, right? It's like I had two iPhones, both of them were in the background, they couldn't establish a connection. For the purposes of our building this network, they wouldn't know they were around each other. But because of the presence of a Chromebook, the Chromebook linked both, and suddenly they're at distance 2. Is that a real problem? Not really, because we actually are just trying to tell you the general flow of the disease towards you. So we're effectively, in any high school which wants to use this, we are now completely immune to the iPhone background problem. Just put it on the Chromebooks. Okay, but now there are other things that we also did. Because, so that's the latest. And I wanted to say that just to credit the high school students who came up with this idea. And it's the creativity comes from everywhere. But now, what we ended up doing before that is we have something else that we use, which is the Wi-Fi system. So in fact, if you have an iPhone, even though your app is in the background, it's able to constantly check to say which Wi-Fi access point am I connected to, like which physical access point am I connected to. And then we can check if two of them are on the same one. The reason why other countries didn't use this, like people were really trying to do contact tracing, and many of them gave up and ended up using some other system that Apple and Google made. But the reason they gave up is because they were using a different paradigm. From their paradigm, they cared about identifying people who were around each other, and their purpose of their app was to tell people to quarantine, which, as I said earlier on this, is actually, we realized that's not even the main thing you should be doing anyway. Once you move into the paradigm of just link people up and tell them if maybe it could have been that your housemate's co-worker's classmate got COVID. At that level of resolution, the Wi-Fi router is enough. So we managed to overcome that, and actually that's what we have now. And we have people in the office. I have an office over here. We have people in the office. Basically, all of them use iPhones. I'm the only one with an Android. But now nobody needs to do anything. The app is actually just working on the iPhones. Did that answer your question?
Yes, it did. That's
Yes.
super interesting.
Yes, and this is like Carnegie Mellon innovation here, right? So I do encourage you, if you held back from the app because you were like, I'm an iPhone user, too complicated, not true anymore. You should get it. Okay, and it looked like there was a question. Is it Erica?
Oh, yeah. I was just going to ask, like, you were talking about how you can kind of trace connections and like, oh, this person might have tested positive and now I know to be careful. But I was just wondering, is the likelihood that like once they test positive that you would have gotten it already? Like, how do you deal with that? Or is it more like you would be finding out before you actually have a risk that you would have it yourself?
Okay, that's a great question, right? So the question here is about how, if you have this, if you find, what's the value of finding out that someone so far away had the virus? I mean, the chance that you will get it from them is actually not 100%. In fact, it's very low, right? The chance that, well, actually, I shouldn't say it's very low because they might spend time with other people who spend time with other people and so on, right? So the way to think of this is that we're actually not asking you to quarantine. We're actually trying to ask you, we're trying to tell you when you might want to be more careful. And the difference between these two is it doesn't cost as much to be more careful. It costs a lot to quarantine. I'm not referring to dollars costs. I just mean like even, do you want to quarantine? It's a big ask, right? And so what we're really asking for is to have people be more careful in the general vicinity of every positive case. Not necessarily because they would definitely get infected, but because it just lets them know this is a good time to put up the guard. And in fact, people these days are trying to do research to say, suppose that you have the situation where all around in this area, everyone's wearing a mask. What happens to the transmission probabilities? They actually drop. And so what we're trying to do is we're trying to control the R0 of the virus, this basic reproduction rate, like how many people get infected from each infected case. This is a totally different way of controlling that. The way you do that is you just make it so that in every vicinity of the positive case, people are just acting a little bit more paranoid. And a little bit more paranoid might actually make a big difference in trying to reduce the spread. So it's not that they were definitely going to get infected through that particular person. However, it is something to probably care enough about to say, maybe I do want to wear a mask, or maybe if I'm about to go to a gathering with 100 people, well, maybe I don't want to go to that gathering with 100 people anymore, right? Because you see, why I said 100 people is because if there's that one person who's positive, if that person ends up also going to also going to events with like 100 people, that positive case could actually go and multiply and be a lot more positive cases, which could then get around to you. Oh, another thing to be careful of, it's because every time you get a positive test, as we know, there's a delay between when you actually got the test and when you get the results. So actually a distance 3 is a cause for caution, because there could be people already at distance 2 from you who are already positive. Ultimately, our app is designed in a way which it kind of reverses the incentive structure. Our app is designed in a way so that if you don't want to get sick, it helps you not get sick. It's not like every other system, which is designed to not directly help you, but it's designed to be, other systems are like, if you get sick, we'll kind of make sure that nobody else gets sick from you, if that makes sense.
Question.
Yeah.
How often does the app send out or listen for beeps, and did you run into the problem of that getting battery usage intensive?
Thanks for asking. Yeah, the question was like, how often does the app send out these kinds of pings to go look for nearby devices? Will it run into a battery issue? Okay, so because we aren't Apple and we aren't Google, we don't have control of a lot of things in the operating system, and so we pay very close attention to what you have to do in order to keep your app running before the operating system kicks you out. If you make an app that's doing a lot of crazy computation and using a lot of battery, the operating system actually just kills your app. So in fact, we actually only scan for nearby devices every 7 to 8 minutes. And the 7 to 8 minutes turned out to be okay because, first of all, that was the requirement from Google. I believe that was the one. If you do it too frequently, they'll shut you off. And 7 to 8 minutes was okay because we were interested in trying to find out whether or not people had been around for 15 minutes. And so the way we figure that out is we go and do a ping, and then we do another ping, and then we do a third ping. And it's like if you've been around for 3 pings, then you've been around. You've been around for maybe about 15 minutes. We do something more sophisticated than that, actually. It's like we basically, you can think of the pings as plotting dots on a graph, if that makes sense. And then we connect the dots of the graph by, or not connect, but look, we make a function. We make a function which says for any given time, how far were you from the other person? The dots are, we measure that at this particular time, you were that far. At this other time, you were that far. And at this other time, you were that far. And then we kind of connect the dots. Right. But so we actually only ping about every 7 to 8 minutes. Consequently, that makes the battery usage really, really, really good because it's not constantly doing things. And a good rule of thumb, by the way, is what's involved in doing this. Most of the time, the app's doing nothing. And then it kind of wakes up and does a few scans, a few checks, and then it goes back to sleep. So as a fraction of how much it's using the battery life, it's very little. If you happen to use an iPhone, it uses even less, and that's because the iPhone is not able to do its own active scanning, and it's not even able to itself scan with Bluetooth. It can only respond if someone contacts it. Are there other questions? I'm looking here. So I'm trying to see if there are other questions here, which were maybe in the chat that I didn't get yet. If if it only, my vision is just not very good.
Sure. Do you guys have a lot of adoption outside of universities and schools?
Oh, that's a good question. So we do have random people who have downloaded the app outside. In fact, we hit something like 80,000 downloads, but that is not directly useful because if people are downloading the app and they're kind of sporadically scattered, you don't build this critical mass. That's why the thing I shared was the first university deployment that we made, Georgia Tech, like boom, we saw this phase transition. That's actually what it's called in random graph theory. We saw the phase transition happen, and then suddenly you had this like enormous connected component, which was extremely exciting, right? That's actually the goal of the app. And so our model right now is that we're trying to reach out to universities, to schools, and to other of these dense environments so that in those dense environments, people can see it's useful. In fact, it's really neat. Like after giving a bunch of these talks, it turned out that a bunch of high school math teams decided to get interested in this, and they started to run their own campaigns. One even started a change.org petition to get their students and their district behind this. But we expect it to roll out in schools first. And as it rolls out in schools and proves that it's useful, we actually expect that it's going to expand into the community because of the fact that we've done this reversal on the incentive structure, right? Like by making an app that's actually directly useful to you, if people found out that there's an app that they could use and the app is going to help them avoid getting sick, and also all of these people are on it already, suddenly there's a lot of value. Suppose you work in a restaurant across the street from the university. You have a lot of value to install the app. Or if you happen to live with somebody who's a teacher at the school, and the teacher at the school has the app, and the school's on the app, it actually would be quite useful for you to have the app too, because then you'd get information. So we actually expect it to spider out from those core points. But ultimately, what we're really trying to do with this is we're just trying to prove that this is actually going to be the most powerful way to fight disease. Because now that you understand the concept, it's basically radar for disease. And up until this point, it was not possible to have a radar for disease because there weren't enough phones around. There weren't enough mobile devices that could help you to build this kind of a network. And what the case is that we're making the case that in the 21st century and forever onward, if you ever have a pandemic or an infectious disease, the most powerful tool to reduce the spread of it is to give everyone a personal radar system. That's what we're trying to prove. And if we can prove that, actually then this thing should roll all over the whole country and the world. And then we should have no more of these infectious diseases. Ooh, more questions. Erica, you have a question. My vision is bad. Can you maybe let me know what your question was?
Oh, okay. I was just wondering, in terms of the spread of the app and trying to get more people involved, have people been resistant to using the app, or do they just not know about it because like word hasn't gotten out? Because like I was kind of surprised that more people wouldn't download it, especially at CMU, right? Like I think there's another question about that too.
Yeah. I mean, the question here is like, your question was like, is it that people aren't downloading it because they don't like it, or is it because they don't understand it? And that's why I'm holding this session here for CMU students. It's actually because they don't understand it. In fact, most people, when they heard that we were making an app, assumed that we were making the old-fashioned kind of app that everyone else in the whole world is making. And most people in their heads were saying, I'm not sure I want to download an app that will track me and then tell me to quarantine when I've been around somebody else. No thanks. And then they didn't look any further. That's why it's really important for us to communicate to people. That's the old generation of apps. We are the first next generation app. And in fact, the only people who came up with this idea. And when we're talking to people to explain, we have to explain it's a radar. It's for you to track COVID. And once people understand this, we've noticed that people are generally quite positive. Actually yesterday, the Georgia Tech student newspaper wrote, their editorial staff got together and made a consensus opinion where they said, we think this thing is actually valuable. Right? And so what we're trying to do now at Carnegie Mellon, for example, a highly technical group, it's that we're trying to help as many people as possible know that this is actually a fundamentally more powerful system than you may have ever heard of before. And there's no cost. It directly helps you. Why not? And not just why not, it's like, No, why not is the wrong answer. Why not is like if you had something that was bad. Not bad, it was like, why not? Why not? No trouble. This is like, this could be enormously powerful, because if we start seeing cases in CMU, if you want to make sure that you also don't get sick, it's extraordinarily powerful to be able to avoid. In fact, we expect this thing, as people start to understand it, to have the same kind of value proposition as being able to look at the satellite image of a hurricane coming towards the coast. It's like today we're like, of course we want to use that. We want to see the hurricanes coming. But I was quite curious. I looked at the history. Like 200 years ago, if you lived on the coast where hurricanes went, you just died when a hurricane came. Nobody knew that hurricanes were coming. It's just like you're living in your way and it's like, oh, wind's getting big. Wow, the surf's getting big. Oh no, it was a hurricane. End of story. But now we're like, oh yeah, hurricanes. Well, of course, use the satellite. I mean, you should. The Mongolians, when they were trying to invade Japan back like twice, they tried to invade Japan and their fleet got sunk by the cyclones, right? Obviously, they should have just checked the radar, right? Like if they had checked the radar, they'd have been fine, and then they'd have invaded Japan. But of course, it's like there was no radar. So we basically expect that as people understand what it is, our experience is that every single student organization, even like fraternity groups, sorority groups, anyone that we explain what it is, once they ask enough questions and understand it, they usually walk away being like, actually, this thing is legit. This is actually really useful. And it's not like all of the other things. But our problem is that the world is saturated with all of the other things, and everyone assumes it's that. So we hope that now that you understand what it is, if you live in a dorm, or if you know other people who are at CMU, or if you are at a high school and watching this and you want this to be used, we actually need that people like you explain to other people what it does. And if you do so, it's going to cause that explosion to build that mountain of people all using the system. We have generally not found anyone at the end who's like reluctant just on principle. Daniel.
Have you thought about making graphics to maybe just like present to clear up some of these misconceptions, or just like good visualizations?
That's a great question. Like making graphics, have we considered making graphics or like posters or something, visualizations to show people how it's different? We are actually working on that now. And so if you live in CMU housing, you might soon find some posters on the wall. This is actually what we're putting out. We on our team are also always trying to make things that we put on our social media, but there's a little bit of a chicken and egg problem that we have always thought about. It's like if we put it on our social media, you know who's following us? Our fans. so how do we get it to the people who don't know what this is? And that's how we got a new idea. In fact, you're among the first people to find out or to hear this. Well, actually, no, I think CMU already put it up. But now people who are in the CMU area, if you're using the app is also going to provide discounts to local restaurants. So this is also fun because we have a user experience team, right? So I come from the math and the algorithm side and came up with some of these core ideas, but I knew that they would never go anywhere if you don't have a user experience team to make it something that aligns with people's behavior. So we asked, one of our team members thought about it, a bunch of our team members thought about it, and they were like, what do students really need? And what's like one of the biggest things that would get students interested in something? And the answer was like free food. And as soon as they said that, I was like, that's totally true. I was a graduate student. The way I survived was always, if you hear there's free food, oh my gosh, I'll go to any seminar in the world. I had a friend in graduate school who was so good at free food, he would like be able to not buy food the entire week. He just knew like which places had the leftover food from various campus events. Anyway, so what we ended up doing is once we got this idea, we were like, oh my gosh, it works. Because you know who's really suffering right now in the pandemic? Restaurants. It's true. If you walk down the street, the restaurants are all shut. I mean, not all shut, but there's all these restaurants that have gone out of business because nobody's getting food. So we were like, aha, you got restaurants which want students to buy food. You got students who want food. So the new thing, the new app at CMU, actually no, I don't know if it's up yet because we have the first restaurant already we've been working with to put a discount on. But if you happen to have the app in the CMU community, it actually shows up in the CMU community announcement, and we'll put like these various restaurant discounts inside there. So yes. So how we got here, by the way, is because you talked about graphics. So basically, those posters that are going on the walls, they not only explain how NOVID works, they also, I think, have a picture of a hamburger on them or something like that. So anyway, we try everything.
Since the the Sunday Putnam seminar is cancelled, is Little Asia going to be one of the restaurants?
You have a great question, right? Because it actually wasn't just Little Asia. I think it was Bengal Kebab that we were keeping in business. There was a particular restaurant that we always went to after the Sunday Putnam classes, and on many of those days, we were basically like their only customers for the night. So your question is like, are we working with them? That's a great idea. We actually started by just contacting the restaurants that a person on our team was friends with. We have a person on our team who happens to have knows a bunch of restaurant owners. But based on our experience, it seems like every restaurant we contacted was like, wait a second, you're telling us that we can advertise with our discounts for free on your app? There's no catch? And we were like, well, we're not trying to make money on this. We're just trying to help people. And they were like, and it's free? Yeah, it's free. So ultimately what's happening here is it's a win-win-win scenario on everyone's side, because then we build the CMU community, the restaurants get this free way to reach out to students get food. Yeah, that's what we're doing. And yeah, we'll probably reach out to Bengal Kebab as well. They're good stuff. More questions. Oh, I see. I'm going to hit something that went onto the YouTube side because I saw somebody asked. I'm sorry if I took forever to answer your question. But you said, can I give you a summary for you to give to friends and teachers so that they can understand? Because I can understand, but I'm not the best at explaining. That's a wonderful comment. I'm just going to say what we have noticed happen for any group which is trying to have this thing grow in their area, if it's a high school group. My immediate advice is find about 10 other people who are also interested. The first thing is to get about 10 other students who are interested. And then once you have the 10 other students who are interested, you can start advancing. And if anyone's watching this, whether live or afterwards, if you're interested in working with us, just go to the NOVID website, novid.org, and there's a contact form which you can use to contact us. And actually, if you're interested in having this thing grow in your area, just use that contact form, contact us, we'll reply. And then we're going to try to help you find a way we'll guide you to build up this community. And actually the model of how this should be done, I think, is what one of these student groups did, which is that one person got really interested, contacted us, and then we guided that person to build a team. And as they built their team, then eventually they took matters into their own hands, made a change.org petition, and now they're rolling. More questions. Oh, somebody asked what's the CMU community code. That's called Tartans, obviously, for anyone at CMU. It's TARTANS. If you happen to have the app, you just go and you go to the settings, which is one of the tabs on the bottom, scroll to the bottom of the settings, and then just type Tartans. It's automatically all caps. And I'm not sure if the advert for that particular restaurant is in it yet tonight. We were waiting to get we just messaged the owner telling them that CMU gave us the all clear. More questions. This has basically run over to the full hour at this point, but if there are any random questions, I'm happy to just take them at the end.
I asked in the chat, but like about what you said of phones using like Wi-Fi hotspots. Should like people be using Wi-Fi's instead of their mobile data for the app to work better?
Ooh, that's a great question. It's like since we're sensing like proximity using Wi-Fi, is it better if you have your Wi-Fi connected as opposed to your mobile data? The way I would say this is, actually, in general, I usually have my phone set up so that if I have any nearby Wi-Fi, it automatically connects. So our advice would be to leave your Wi-Fi on so that if you're on campus, it just connects up to the local Wi-Fi. And if you're off campus, you use your mobile data, as opposed to just leaving it on always mobile data. That would be my advice. The good news, though, is again, this is the fun of the math behind this. In the CMU campus, there are so many people that there's probably somebody with an Android phone within range. You see, the value of this is, you can think of this as we're building this network with all these different sensing methods, and your real goal is just to plug in somehow. And the way that you plug in is that there's someone who plugs into you who's nearby. And if it happens to be an Android device, then done. But of course, if you have a choice, just leave the Wi-Fi on, and then it'll auto-connect, and you'll be fine. Or if you use an Android, don't do anything, it just works. Cool. Any other last questions?
Are there any ongoing challenges you guys are still working on?
Oh, wow. Yes. Are there any ongoing challenges we're still working on? Well, as I commented, we just discovered the idea of making the app work on Chromebooks. That became a big bunch of work. And so suddenly more fun toys got brought into the office to go and experiment. Like this office is full of like random phones and Chromebooks and equipment and whatnot by now, right? So that's one kind of technical challenge. Another kind of technical challenge is we're actually always interested in trying to understand better how well our systems are working, because we're sensing with all these different methods. But then to be able to get a sense of like, okay, so people are using Wi-Fi, are they really connecting, right? Like that's data analysis. We have like gigabytes and gigabytes of data that are coming in. We don't actually know who people are, but we just have this data saying like the typical phone has this much Wi-Fi connection and this much Bluetooth connection. There's a lot of analysis there. That's the stuff we're doing right now. We're also doing stuff on the app development side. We're like adding a QR code scanner so that it'll be even easier to input data into the app. Also, in some places, they want, not they want, but like if you're going to use this in some situations, it's useful to be able to scan a QR code to like check into a location. For example, if you are a parent dropping your kid off at school, you as the parent don't want to hang out in that classroom for 15 minutes for your phone to connect, but you might want to be like, well, my kid is 5. I'm not going to give my 5-year-old a phone. If I give him a phone, the phone might not come home, right? Like, well, actually, I'm not sure that's true. Maybe the 5-year-old will be like, this is a phone, this is awesome, and the phone does come home. But anyway, it's just like they might want to scan a QR code to be able to do something. So we're building that. That's software engineering. But since, Daniel, you have a pretty strong technical background, I'll say that the most exciting part, from my point of view, is the next phase, which we haven't started yet. I didn't start this just to build an app. As you know, I'm actually not just a guy who's like, I just want to build an app to build an app. No, I got involved in this in March when I saw COVID expanding around the world, and I was like, how come no one's using network theory to try to track this spread of this virus and put it out? So I started this because I said we need to have an anonymous network of all of this like interactions happening worldwide. And on this anonymous network, we need to understand the dynamics of how COVID spreads. So actually, that's what we're really interested in doing. There's a gigantic network computation problem. And as we're talking to certain regions, governments of regions, they're actually interested for that perspective. Because, for example, there will be a vaccine soon. How will we know if the vaccine works? Well, I mean, you could be like, well, we gave it and hopefully it worked. But one great way to know if it worked is if your entire region, this is now government perspective, if the whole region's on NOVID, and then now if people who are getting the vaccine are able to confirm that inside their app in some secure way, you would then be able to find out if they're getting infected. Does that sort of make sense? It's like, this is actually extremely important, by the way, because if you're going to roll out a vaccination program, hopefully we'll get information about effectiveness. And unlike usual situations in the past where you test your vaccine for like years before you roll it out, here we're basically rolling it out and hopefully getting information at the same time. So that's actually a really interesting network theory problem. We constantly have these kinds of algorithmic problems of like, if I have a huge n for the number of vertices in this graph, can I efficiently compute something about the graph without running out of memory and without running out of CPU time? Yeah. Cool.
Has any like state or federal government talked to you guys about this app?
Yeah, we have. We have actually talked to state governments and also governments of other countries. Some discussions are in deeper stages than others, but one of our disadvantages at the beginning, and even now, is that our approach is fundamentally different from everybody else's. And this is an interesting detail I'm happy to share with you. Someday you guys might also end up working in something that affects lots of people. And if you work in something that affects lots of people, you'll end up talking to governments. And the danger when you make something totally different is that there's a risk involved of what if it doesn't work. And it's actually easier politically for a government to go with an option that everyone else is going with, because even if it doesn't work, no one will blame them for it. Which is a little bit sad. I mean, we actually already have a proof of why the other methods won't work. But unfortunately, it's a safer bet for people to go with the other options because, well, you can always blame someone else. And what we're doing now is that's why the CMU deployment is so important. We're going to prove that this is actually fundamentally what you need to do to solve this problem. Because we already know from our other proof that the other methods won't work. So we know that it's just a matter of like 3 months before everyone finds out that all the things that they chose to do didn't work. At that point, we'll finally have something that we've proven does work, and then we'll be able to go and save everyone else. But it's a sad thing, is that somehow when you come up with something that's actually a paradigm shift, it's really, really hard to get people to accept it. But you see, your audience, I mean, this audience understands, right? This idea of like, isn't it really powerful to get a radar? Yes, it is. It's really powerful to get a radar. And if you got the radar, and if people knew how to use the radar, it's like, boom, you can have people actually avoid getting sick. And that's not even a downside. It's not even like a quarantine-based solution. But anyway, the reason why we keep working is because we know that the other methods will not work. Actually, one reason we know is because Germany started using the other methods like a few months before the US, maybe like 2 to 3 months before. And the recent article in the German newspapers was that it didn't work. And they spent like 25 million euros doing it. So we know that even if you spend a lot of money on the other standard approach, it generally won't work. And so we are just constantly fighting to go and try to make sure that this works. And all of you here at Carnegie Mellon, or all of you who are watching this live stream from your other high schools, anyone who joins this system early is actually going to be part of making history. And my analysis as a mathematician is that this will work, and then we will end up unveiling to the whole world a totally different way of fighting any pandemic in the 21st century. Cool. All right. Well, with that, I should probably close off because I think it's already 6:30 now, and I know people had allocated other things with their time. I hope that you guys had some fun. It was fun. It was nice to be able to talk to all of you about something that's non-Putnam. Now you also got a little window into what I organize part of my life around. And you can also see how like the way of thinking from all of the problem solving and all of the math that I normally do is the same kind of thinking that went into the construction of this system. And my hope is that someday in the future, maybe you'll end up working on something, maybe you'll end up with your own idea. At that time, I might be too old to do something like this. And hopefully one of you will be the one that helps to save the situation at that point. So thank you to everyone. And have a great rest of the day.
Thank you.
Yeah, take care. Bye-bye.
Thank you so much.
Thank you.
Thank you.
Bye-bye. Oh, wow. I just saw on YouTube somebody asked that there was one more question. So I'll hit that question. Again, this is just an answer to the YouTube question. Somebody asked about whether it works on iPads because everyone has an iPad at school. The answer is that on iPads, it doesn't work as well because of the fact that you need to have it always running somehow. So again, if it was Android tablets, I would have said no problem. Android tablets, no problem at all. But if you have iPads, because of the fact that you need something to wake up the iPad, the Apple piece, unfortunately it won't work as well. I wish I had a better answer to you than that. I mean, I'll say, yeah, there are workarounds. You could do something where you went and said, hey, everybody, leave the iPad in standby mode. We've built that. If you're curious at all, feel free to reach out. We're happy to chat with you and explain to you what's involved in that. But it's just not as trivial as like doing it with the Chromebooks. So thanks for asking that question, Simon Miller. Okay, cool. Well, with that, I'm going to say thank you to everyone, and I'll disconnect the YouTube as well. So nice talking to all of you from anyone who joined from around the world. See you. Have a great weekend.